laser cooling of solids. So Professor Dragic is a graduate from UIUC, and he worked on high-power lasers for LiDAR implementations with high-power fiber lasers. He's authored and co-authored more than 200 archival journal and conference papers, has 17 patents, and has been involved with the launch of several startup companies in the realm of optics. So,
cool. Well, thank you. Thanks for the introduction. I guess you can decide after the talk whether you were lucky to have me or not. Okay, yeah. So anyway, I was given a kind of actually I was supposed to have done this last year, I think. But there were a lot of things that happened with scheduling and stuff where I wasn't able to give this talk. I thought it's kind of cool. The topic is neat, no pun intended. Cool. I kind of got into it through a mirroring program. I hadn't done anything with it before that, and we do a little bit with this with cooling, but we are by no means the top tier folks on the planet that do this sort of thing. So what I want to do is just kind of give you an overview of the technology, kind of what it entails, and try to understand that it's not as mysterious really as some people make it out to be. So, okay, so the title of the talk then again is laser cooling of solids. Sometimes this is referred to as optical refrigeration. Specifically, what I'm going to focus on is fluorescence-based cooling mechanisms. And that's going to be the main part of the talk. There are other ways to do this, especially in like gases and other states of matter, but I'm going to stick to that one. Now, that should become apparent very quickly with the talk. Okay, so just to give you a little bit of an outline, I'll do a little bit of a historical background. I think it's really nice to understand where some of these things came from. A couple really neat papers that we pulled out of the literature. We're going to talk a little bit about the basics of laser cooling in solids. We'll talk about the limitations to laser cooling. Why is this such a challenging problem? I'm going to focus mainly on ytterbium doped systems. Those are the ones that are most predominant in the laser cooling field. But I will discuss just a little bit other rare earths, the potential for using those. And then there's a little section that I've got here on records, world record cooling kind of a thing, applications for the technology, and some caveats, and then we'll conclude. All right, so I'm going to start with a little bit of historical background. Just going to keep myself on time. So I don't know. Does anybody here use the word fluorescence? Some people do. It's pretty ubiquitous. Luminescence, photoluminescence, things that you might have heard. This term was coined in 1852 by Stokes. You can see there's a little footnote in this paper that I brought up from the philosophical transactions of the Royal Society of London. So that somebody was using the term fluorspar with regards to some crystal or some material that was making light when with different color when you shine light on it. And he stated, I don't like that word, so what I'm going to do is I'm going to come up with this word called fluorescence that I like better because it sounds like opalescence. It's a term that you normally associated with like opals, where there are layers and things and different colors and depending on how you shine the light, onto it and all that stuff. So in this paper where he coined the term fluorescence, Stokes argued that all the fluorescence, any and all fluorescence, presumably to satisfy the second law of thermodynamics, have to be produced at a voltage lower than where you're exciting it. So if you're pumping it at 1,000 nanometers or some wavelength, the fluorescence has to all be at a wavelength longer than what you're providing to the system. This is called the Stokes shift, okay, that we're all familiar with. So the frequency goes to lower frequencies or energies that are lower. So very, very soon after this, some observations were made where people said, we're seeing luminescence or fluorescence coming out of these objects, but it seems to be violating the Stokes rule. Okay, you're getting, rather than getting energy reduction, somehow you're getting an energy increase. And so you can see in this context then, if Stokes said, well, everything has to be at an energy less than, if you see something that's at an energy greater than, then you're anti-Stokes, right? So that's kind of where the term, the context actually makes a whole lot of sense, okay? So, make sure I do this in the right direction. Okay, so in 1929, a fellow by the name of Pringsheim, this was in Germany. He proposed an experiment in which sodium vapor can be used to demonstrate anti-Stokes fluorescence. This is the paper here. It's in German. There was a time, pre-wars, that German was the language of science. That changed after the wars, and at least thankfully for me, having been born in the U.S., I speak English and I don't have to learn German. I learned Spanish in high school instead. But anyway, how would this work? What was this proposal? Well, here's an energy level diagram for sodium. It's a sodium vapor. So you have a little cell, you heat it up, and there's some sodium vapor that's the same ground. For the ground state, to the ground state, there are two transitions from the 2p3 halves level, 2p1 halves level, down to the 2s1 halves level. And so the idea is if you can excite the sodium such that you produce all of these colors, there's going to be, you put a filter in here, you pass the shorter wavelength, and then that shorter wavelength you use to pump yet another cell. Okay? And then, if you have thermalization happening from the 1/2 level to the 3/2 level, and subsequent luminescence, you're creating anti-Stokes fluorescence. Okay? And what you're doing then is taking up photons from the material in order to thermalize from this 1/2 to the 3/2 level. And that means that these levels have to be close enough together such that you have, enough thermalization to that state. And then he's proposed doing a kind of like a heat pump, more or less, such that now you would have laid another dewar. You can then absorb those two wavelengths and then produce the heat that you extracted from the first system. Okay, but even that's not necessary. All that was needed was to show that you can do this. There were results contradicting the Stokes Law. Okay, again, that all fluorescence has to be Stokes rather than anti-Stokes. They were being published. People were publishing their observations even before Pringsheim. This immediately drew controversy because Naysayers had claimed that it violated the Second Law of Thermodynamics. Again, negative changes in entropy are not permitted. Okay, so what that means is, for instance, if you have a heat bath and you have a cold bath, when they're somehow connected, the heat will propagate in this direction. Okay, that process isn't reversible unless you put energy into the system. You have to put work in order to bring the hot back to the cold, back to the other side. Okay, so that's a system that's not reversible, and then that satisfies the Second Law of Thermodynamics. Okay, so examples pretty well known. This one was just before Pringsheim published his paper. This is a paper by Leonard, also in a German Handbuch der Physik or whatever. And so it's like, oh no, this can't be, okay? And then there's just controversy that kept going for several years through the wars. And then in 1946, a person by the name of Vavilov, which I can't find where I can pull this paper down. So I don't know what this person's first name is, but this group tried to explain, here is why you cannot have anti-Stokes fluorescence, because it doesn't satisfy the Second Law of Thermodynamics. Okay. Now this paper then inspired Landau. Okay, and Landau said, then he's of course in Moscow, and that's Landau and Lifshitz, the same person if you're familiar with the series of books and things. He said, well, let me do this calculation and see if it makes any sense, whether or not, Well, what happened was he concluded, and this is in this paper here, 1946, that the Second Law is not violated as a result of anti-Stokes fluorescence cooling. So basically, the way that I hear people describe it is, you're putting light in and you're creating fluorescence. Maybe you're extracting some heat, but you can't go out there and grab those photons, put them back into the material, and have a laser beam come back out. Right? So it's clear that it's not a reversible process. Okay, well, unless you put more work into it. You can create a new beam, you can harness some of those fluorescence photons, but you're going to put more energy in to create the initial beam. So that's interesting. So this inspired people to try and figure out, how do we actually demonstrate this process? Okay, people tried in all kinds of places, ways, materials, states of matter, gases. People tried liquids. That didn't work very well at all. In solids, for instance, Hansch and Shallow, a couple of famous names, Nobel Prizes and things like this, right? They actually also wrote a paper about how it should be possible to cool gases by laser radiation. Again, you're pumping and it's going to fluoresce, and that fluorescence carries thermal energy away. Okay, they're not the first ones to suggest this. Okay, that in fact, you know, they were more like a supportive role in this paper, so they didn't show anything in this work. But it's an interesting example of people that are now famous, interested in this sort of stuff. Okay, so other examples. So here's an early one from 1968, optical refrigeration, anti-doped yttrium aluminum garnet. Those of you that might be familiar with neodymium doped yttrium aluminum garnet, actually a little bit of it is in this laser pointer. This is a misleading title, okay, because they say optical refrigeration. They didn't actually cause net cooling. You know, what they did was they caused less heating. So you know, it really wasn't that. You know, sure, it's a step forward, but there were lots and lots of these demonstrations. But there was no, you know, how do we get net cooling where we go below room temperature, or some, you know, some sort of rubric that way. In 1981, that changed. In 1981, I don't know how to pronounce this, but Joe, maybe, or Whitney, cooled, not in a solid, but they were able to cool carbon dioxide, okay? And the way that they did that was, here's an energy level of carbon dioxide. Again, carbon dioxide is a CO2 molecule, so, you know, the oxygens are doing this, right? And then the molecules spinning around in circles. I don't want to get myself dizzy, but that's kind of what's, you know, those are the states, and those are low energy states. Carbon dioxide is known to produce a 10 micron wavelength, and if you're familiar with black body radiation, that's room temperature, basically, okay? So it's a heat laser, basically. So what do they do? So the first thing is they recognize wave of ground state. There's a first excited state. This is about 1,382 inverse centimeters, okay? This energy difference. It's not a huge value, but it's rather large, okay? So what they did was they said, okay, well, if we have thermal population in this level, from this level, we could pump with a 10.6 micron laser, go to the 001 level, and when it lasers, or not lasers, it produces light, it's not lasing. I'm confusing 455 with this. We're not lasing at all here. Transition from 001 to 000 produces a 4.3 micron photon, thereby extracting whatever thermal energy was used to populate this level, okay? What they did, of course, they heated it a little bit. You'll notice, you know, the temperature change, you know, or this population that you have is going to be based on Boltzmann statistics, and that depends on KT. And so the larger the KT values that you have, the higher the population at this level. So they raised the temperature to like, I think it was 300 Celsius where they were operating, so roughly double room temperature. So this was then the first like reputable demonstration of laser-based cooling. Okay, now the title of the talk, of course, is you know, cooling of solids, not of gases. So when was the first net cooling in a solid observed? Remember, I showed that paper in '68 using this material. It was in 1995 by a group at Los Alamos National Lab in Mexico, led by Richard Epstein. Okay, and what they did was they took some ytterbium, they stuck it into Z-bland P glass. Z-bland P is a zirconium, barium, lanthanum, aluminum, sodium, lead fluoride glass. It's a heavy metal glass, which actually, interestingly enough, was accidentally discovered in France in 1974. These fluoride glasses it was a serendipitous thing, just a bunch of concoctions of things that they put into this crucible, and at the end they came back to it and it was like there was a glass there. So it was weird. But anyway, what you do is you dope this with ytterbium. Now I'm going to stick with the trivalent rare earths during this talk. So you'll notice YBF3. YBF2 also exists. There's divalent rare earths as well. It just depends on, you know, how it bonds into the system and all that stuff. But the spectroscopy is completely different. Okay, so the spectroscopy of YB2 plus is very, very different from YB3 plus. And you can't do cooling in YB2 plus. I don't have that. It's beyond the scope of this talk. But if anybody wants to learn more about it, come talk to me about it. Okay, so it turns out there's no good reason why this material should have been able to be used for cooling. And the reason for this is, you know, this glass has so much stuff in it It's not made conventional, with optical fibers, for example. Where some things are at high temperature and the vapor pressures and impurities kind of run away and all these things. With this glass, it's like melting crucible, right? You take your starting materials, which probably are crystals in this case, put it into the crucible, you melt it, to some temperature, and then you cool it very slowly or fast, depending on what you're trying to accomplish. But this almost always has impurities in it. And as I'll talk about later, impurities end up being, just the dead stop for the ability to do cooling at all. Okay, so there's no reason why this should have worked, but it did for whatever reason. Okay, so we've gotten now to 1995, and we've demonstrated the first, Epstein and company has demonstrated the first cooling in solids. I want to kind of step to the side a little bit and talk a little bit more about the basics of laser cooling of solids. So you kind of see, kind of where that comes from and what are some of the issues and things like that. So, okay, again, I want to reiterate. I said lasing, so I lose at least 3 points for today's lecture. There's no stimulated emission in this process, and in principle, you cannot get gain at a wavelength that's shorter than where you're pumping. Okay. We can prove this many different ways. Probably the easiest way to do it is just pick up any sort of emission absorption cross sections for any material and see if you can find a combination of wavelengths where gain becomes possible for any inversion. Okay, it's just not. Okay, you can't do it. So again, we're not going to do simulated emission, just spontaneous emission. So again, to put energy level diagrams to things, we have, say, for example, a 3-level system. We might pump up to this upper state. We might get some non-radiant relaxation. This is heating, and then a fluorescence photon from this level to that level. And that's the normal Stokes process. Okay. The anti-Stokes process, this results in photon creation. The anti-Stokes process results in photon annihilation. And so what happens here, of course, if you start at ground state, if you have enough temperature, or your KT is large enough, and you have population in this level, you can pump out of this level to the top level, and then you can have a fluorescence path from the top to the bottom level. Okay, and so you're taking away photons simply by populating the upper state thermally. Okay, so again, you can have a path that goes this way, and this is exactly what the CO2 system did. It just turned out that the branching ratio for the 4.3 microns was favored over going back to that upper state transition that was pumped from at 10 microns. Okay, ytterbium. Sounds like I've been saying this this name quite a bit. And so what I wanted to do is just to kind of talk a little bit about its energy level diagram to put this into a greater context. Because there's no other solid except for these ytterbium doped materials that do as well as ytterbium. So, thulium, demonstrated cooling in thulium system, it's not as good. Other rare earths, and as we'll talk about, there's no cooling demonstrated at all, ever. There's reasons for this, but this turned out to be a magic material. Part of it has to do with its energy level, simple energy level diagram. There's only 2 levels. Okay, this has one unpaired spin in its orbital diagram, and so it's just how that thing changes, in terms of its configuration. So there's only 2 levels. There's only 2 states. Okay. There are degeneracies though. So there's 5 halves and 7 halves. So this, if you remember, this is the J quantum number, the total angular momentum. You add a half to this, add half to that. That's the number of levels. So 3 and 4. And so I have this drawn to the right over here. So this, I'm showing 3 levels and 4 levels. Why are they split? Well, it's that each of the degeneracy here is broken by the host itself. Okay, so even though, like in a vacuum, for instance, this may have 2 levels that are, have their own degeneracy, 3 and 4. Once you put it in a host, the host itself and the field that it impacts or imparts upon the rare earth will no longer it'll bring the degeneracy and split this the single level into what we call manifold. That's Stark splitting. It's electric field effect. Okay. Now, what's interesting about this is the rare earths aren't impacted very strongly by the host. Meaning that, like, if you put ytterbium into this, into that, and into this other thing, you get a wavelength that's around 1 micron. Okay, it has to do with the outer shells that are outside of where these transitions take place, shielding the ion from its external environment. For example, some of you may be familiar with titanium sapphire lasers. They produce 800 nanometers, peak 850 or whatever. You take that same titanium, you put it into like spinel, which is a magnesium aluminate. The peak wavelength's in the blue someplace. Okay, so it just depends on what you put it in. So rare earths don't do this. So like erbium is the same. So like erbium makes 1550. It doesn't matter what you put it into, it'll make something like 1550, but the spectra will be slightly different based on the host's impact on the breaking of the degeneracies. And so just to show kind of how that works, this is meaningful for effective cooling. Aluminosilicate energy level diagram looks something like this. With the splitting, this is like crystal splitting. And then like phosphosilicate, I'm making these glasses, but you'll see the energy spacing here is a little bit less than it is for the aluminosilicates. That means something. Okay. The other thing, of course, we want to think about are the resulting spectra. Okay, so because we have these solids that are impacting the emission spectrum of the active ion, we have to consider that sort of in our analysis of whether or not something may or may not cool, or why it does or doesn't cool. Okay. Anyway, what I have here then shown, again, this is the same diagram from the previous slide, is plots of the absorption and emission cross sections. Okay. This is not the same as the luminescent spectrum, but it's close enough. Okay. You'll see that this changes quite a bit depending on what the host material is. Okay. But the idea is you want to pump with a low energy, and you want to emit with a long energy, okay, or higher energy. So if you look at this, you could pump anywhere where there's an absorption coefficient that's a cross section that's non-zero. Actually, it goes basically to zero, and we can absorb anywhere in here. So for instance, if we pump at 1025, that's over here someplace. You'll see the fluorescence spectrum, which is independent of the pumping wavelength. Again, anti-Stokes is possible. You get a significant amount of power or luminescence that's at a wavelength or an energy that's higher than where you're pumping. Okay. And again, if we're pumping at 900 nanometers, okay, and at 900 nanometers there's no emission, there's no way that we can cool the system. You're always going to produce photons at an energy that's less than where you started. Whereas you start marching this way, and again, this fluorescence spectrum is independent of where you pump, as it turns out. If you choose a pumping wavelength out here someplace, then you can produce this entire spectrum, which is almost entirely anti-Stokes, and you're extracting energy. The trade-off, of course, is as one marches towards longer wavelengths, even above 1050, the absorption is so low, okay, that you need large volumes of material in order to absorb sufficient power to actually see any appreciable cooling. Okay, so those are the spectra, the emission absorption cross sections, and hopefully that gave all of you a little bit of respect for like what the what that looks like. Okay, so how then do we actually quantify whether we're in a state where we're anti-Stokes fluorescence? Okay, so here is just an example of some measured data. This is I believe this is a fluorosilicate glass that we did this with. We were pumping at 1020, okay, and this is the spectrum that we produced. Okay, so you'll notice that there's a lot of anti-Stokes stuff going on over here. Okay, but how much? Okay, so what we do is identify. The first step is to identify the average spontaneous emission wavelength. Okay, and that's how we determine an average energy of the system. And that's just like taking the average of any function, weighted average against some value that you're looking to in this case, the wavelength. I don't have this going from -infinity to infinity. For ytterbium, you can do this because there's only the two transitions. But if there are multiple transitions, you don't want to take an average across all of the transitions. It doesn't make any sense. It's just the one that you're interested in and exciting. So this is the average. This is the average emission wavelength, and then we can define a quantum defect. So a quantum defect that we usually think about in laser systems, you're pumping at one wavelength. You're lasing at a longer wavelength. There's an energy difference between the photons that are going in versus what are coming out, and that percentage change is the quantum defect. And it's positive because we make heat. It's our reference, how we define this thing. But in this case, if our mean wavelength is less than the pumping wavelength, or we'll call it a single frequency if we want to, divided by the mean fluorescence wavelength, this becomes negative as long as this number is bigger than that number. Okay. How much? Well, it's defined by the quantum defect. Okay. That's the amount of energy that we're taking from the system. Okay. We're taking it, again, it's thermal energy we're pulling out of the solid. Okay, all right, so, okay, that's great. I'm pumping it and I'm getting some stuff out, but what's actually happening during the process? Okay, this is the tricky part. There's some papers out there that describe this a little bit. Most of them are just show results. You know, you have this 100-watt laser and you shine it at some crystal and it cools down, you know. But what's happening during the process? So to give you some insight into that, basically, what I have drawn here are the two manifolds for ytterbium. I'm just ignoring all the lines that are in there. That's not necessary. For a crystal, those lines are very well defined. In a glass, for instance, like Z-bland or Z-bland P, the emission spectrum that you would normally see from a crystal is smeared out because of the amorphous nature of the material. So what happens is, you know, this ion isn't the, you know, in a crystal, this ion is the exact same as this ion, is the exact same as this ion. They always see the same exact network. Whereas in a glass, you know, this ion is a little bit different than this ion because I might be closer to a silicon, I might be closer to that or this, and they impact things a little bit differently. So Stark splitting is different. But anyway, I guess this has a general kind of smeared out block. So how does this work? You start out in sort of in the ground state. We do a low energy pumping, and so we might pump from somewhere at the top of this bottom band to the bottom or towards the bottom of the top band. Okay, so that's our low energy pumping. And then what happens is Boltzmann takes over. Okay, you're going to naturally come to some steady state distribution in the upper state where phonons are either lost or gained depending on what you pump to in order to fulfill the Boltzmann distribution in that manifold. If you pump to the bottom of the manifold, you're going to take up phonons in order to achieve that Boltzmann distribution. And I've got this generalized, it's just a line up here. It's not entirely correct, but it's okay. All right, so this actually is the process of cooling. The cooling isn't the fact that you've produced a photon. The cooling happens when Boltzmann takes over for you, okay? And then what happens is you spit out the photon, okay, that's at an energy that's higher than where you pumped. That's when the energy is carried away from the solid. Okay, that's not cooling. The actual cooling, the change in temperatures here, this permanently removes that energy from the crystal, okay, or from the glass and solid. Okay, and then of course, depending on you know where you're pumping from and all these neat things, you might have something that happens down here. Okay, the idea is that this could also be a cooling mechanism, but it could also be a heating mechanism. You know, if this were down here and this were up above, there's some heating. But so what you're doing is you're taking phonons, then you're making phonons. You just want to make less than what you're taking out. That's all. Okay. All right. So what we've said was that the average emission wavelength matters because that gives you a sense of the quantum defect. The negative quantum defect is like the cooling efficiency. That ends up being the quantum limited cooling efficiency that you can achieve. And it's also the quantum limited, you know, for example, related to quantum limited slope efficiency that you get in a laser system. I mean, these are all these things are related to each other. So if you look at different glasses, for instance, these are glasses. Of course, we work in glass, but you know you can pick up any set of crystals that you want, and you can calculate these average emission wavelengths. So as it turns out, for more covalently bonded systems, you have a longer emission wavelength. For systems that appear more ionic to the dopant, you get shorter wavelength emission that's a little bit narrower. Okay, and so you see, I mean, the average emission wavelength changes quite a bit. Okay, but our maximum cooling efficiency calculated from this, between we're pumping at 1020, of course we can pump at 1030, 1040, you know, whatever, as long as we could absorb it, are actually quite low. Okay, so these efficiencies aren't that good. Okay, and again, this is the best that you can ever do. Okay. So what's happening basically is if you put in a photon, you know, you're only getting an improvement of a couple of percent, okay, for that photon that you're putting in. You're getting it back out. Okay, it's coming out as fluorescence, not as stimulated emission, of course. You don't have a beam anymore and all that neat stuff. But this is not it doesn't sound like a great cooler. Okay, it doesn't sound like a great cooler. Okay, it turns out that it's not bad actually. So, okay, and then of course this depends on where you pump. Now, you have to make, when you're doing this calculation, you have to make sure that you have, that absorption available to you. Okay, so again, if this thing isn't absorbed for whatever reason, 1020, all of these do, this isn't going to work at all. Okay. Again, I've focused just on a few ytterbium built materials that are just glass based. If you want to learn more about ytterbium and different materials, do a Google search. Just go on there, Google, tell me about materials, and there's just I did a screenshot of the first few that came up. So I won't go through this in great detail, but all of this analysis holds the same way for all those materials. Okay. Okay, so there's some basics. What I want to do then is talk about limitations to the cooling of solids. What are some of these limitations that one might see? The first one is the saturation of the active dopant. Okay, you're pumping. Let's say you have a finite volume of this material that's got ytterbium in it. You're pumping it, and you have a knob that allows you to crank on the pumping power. Okay, well eventually, what you're waiting for basically, to do this cooling method is for spontaneous emission to happen. Okay. If you're pumping at a rate that's faster than the spontaneous emission that you're producing, you run out of the ability to absorb any more pump power. So at some point you're pumping and your system becomes transparent and you've reached the maximum cooling efficiency possible in the system. Okay? So I've got a plot here that just kind of shows, for some length of gain fiber, or gain material I should say. I keep saying fiber because it's a little worky, but it's generically speaking material. What happens is, for some period of time, we have you're sort of absorbing, you're populating the upper state. At the same time, you have this fluorescence that's occurring. That's of course increasing with the number of photons that are being absorbed. But eventually, you reach the maximum inversion or maximum absorption that you can achieve with the given pump power, and all of your power then your pump becomes transparent. Material is transparent to the pump, and it just runs out the other end of the material. Okay, so you can't continually crank on the pumping power and expect to keep getting anti-fluorescence, because you run out of these ions. So way to get around that, of course, is to have material with more ions. But there are limitations to this that I'll talk about later. Anyway, the upper state lifetime kind of tells us how fast we can cool something, how fast we can extract photons from the system, and thereby thermal energy from the material. But the absorption cross section at the pumping wavelength also sets how fast you can populate the upper state. Okay, so the larger the absorption cross section, the faster you can populate the upper state. It just turns out that for many materials, the product of these cross sections in the lifetime is about constant. Okay, so yeah, you want a nice short constant, time constant perhaps. Well, actually, that's a good thing, right? You want a nice short time constant with a large absorption cross section. So that sounds like an advantage. So there's finding materials that satisfy that condition. All right, so saturation is just at some point you run out of usable YB3 pluses. A short overlay state lifetime lets you dump this energy faster. If one can figure out a way to enhance emission somehow, the spontaneous process, that would be very, very helpful. And the other thing that's kind of interesting about this is that the change in temperature also impacts the spectroscopy. Okay, and we talked about Boltzmann. Remember, this thermal population. So the absorption emission cross sections that we see are due to the Boltzmann population of the ground state. Okay, if the temperature is different, that distribution is different. So what happens ultimately is you get a narrowing of the spectrum and a reduction in the lifetime. And so you actually, as you cool, things get better and better as you cool more and more. So that's kind of a nice, happy thing that happens. Okay, so that's the first limitation. The second limitation is unsaturable background absorption. Okay, so materials like Z-blands and crystals and whatever else normally have impurities, and many of them, the worst ones anyway. Apologies for the busy plot. I pulled this out of a little bit. You plot it. I give it. Are transition metals. So chromium, titanium. There's nickel, iron, cobalt. Okay, they have broad emission spectra covering, the visible to near infrared at these ytterbium wavelengths that are interesting to us. Of course, if we were to operate at a wavelength outside of these bands, we wouldn't have to worry about these things. Yeah, that's just not, but ytterbium is nice because of its spectroscopy. This is unsaturable because they absorb pump photons and they dump them out as heat really fast. And so they become instantaneously available for absorbing again, okay? Now, the worst thing about this, okay, is that, we are absorbing a photon for anti-Stokes fluorescence, and we're emitting a photon with 2% greater energy, okay, or some number like this. This is wiping out a whole photon, okay? So this is really bad, okay? So this is very, very, very deleterious, okay? Anyway, like I said, rapid de-excitation is a non-radial process. Energy is dumped into the creation of phonons really fast. So those impurities are always there, always ready to absorb. And of course, this is a form of heating. Okay, so there's a competition then, the first order of you're doing the anti-Stokes fluorescence, but then you run out of ytterbium emitters. You're cranking on the power. The ytterbium can't absorb anymore. You can't get any more cooling, but the impurities keep absorbing those photons. And so what happens is what was cooling initially turns into heating eventually, okay, with enough power. Okay, another one, stole your data. That's another one, is luminescence quenching. Okay, so are there processes where I excite a rare earth and it decides, I don't want to make light, I'm going to make heat because I'm special, or whatever, I don't know. Some of these things come in the form of high photon energy impurities. De-excitation from an upper level, this is one of the reasons why ytterbium is so nice, is that the energy level difference is like 10,000 inverse centimeters. That's for most materials, that's greater than 10 phonons. And that the probability of a phonon dump is very low. Okay, it's very low in ytterbium. So that's another reason why it's magical. Hydroxyl, for instance, OH, that you might find in glasses, has a phonon energy that's like 4,000 inverse centimeters. Okay, and that's already like 2 phonons to traverse the energy gap for ytterbium. So this is a huge problem. So a lot of work goes into removing this from the solids that might go into cooling. Obviously, where you don't have oxygen, this doesn't matter. But you still find oxygen, OH impurities in even Z-blend fluoride glasses. The other thing, of course, is you can have ion-ion interactions. So in ytterbium, for instance, I could pump it, and I could have all these excited emitters just waiting to make light. Okay. Problem is, rare earths turn out that they play hot potato. They don't like holding energy. They like to pass it. Okay, it's like passing a football or something, or a hot potato, I guess. So what happens is, let's say you have a whole network, a bunch of ytterbiums, they're all close together, and you have one that's excited. Well, that energy is going to go all over the place before it finally fluoresces. Here, the idea is that if you have 2 excited ions finding each other, okay, so like this energy is moving around, you have a ytterbium here that's excited, one over here that's excited. I don't want to hold my energy. He doesn't want to hold his energy. And then you say, okay, I'm going to send you my energy, but I'm going to send you my energy, and the only way to solve this problem is for everybody to just dump everything out as heat. That physical picture actually is kind of what most people refer to in terms of this ion-ion interaction, but I've not seen good, at least physics that I was satisfied with that explains that process very, very well. Okay, so but anyway, this depends on the doping concentration. Okay, so the more ytterbiums you have per unit volume, the more likely that process happens. Okay, so as I said, we can increase the cooling efficiency for a fixed volume by increasing the number of ions. Well, you can't just indefinitely increase the number of ions without expecting that something bad's going to happen as a result, and that's quenching. Okay, the other. I can get to that later with other words. Okay, so at the end of the day, okay, when we talk about what is the cooling efficiency, okay, there are several things that contribute to this. I don't want to explain this equation too much, but you're coming in with a pump, and some of it's being absorbed. A sub Q is the quantum efficiency. This is due to quenching, so if you absorb a photon, what's the probability that should actually spits one out instead of making heat. And then your background absorption is related to impurities or whatever else is going on in the system. Okay, so all of these things matter. For the cooling, that's this part here. We're you know, again, for cooling, we're putting in a photon and getting a photon that's 2% more energetic. It's 2% greater energy or some value like that. Whereas background absorption, ion quenching, and all these effects gobble up whole photons. Okay, so you know, you can already imagine the quantum efficiency in a system like this has to be, you know, if your background is a couple of percent, okay, that which is, you know, pretty good for most cases, has to achieve that value. So you need something that's very, very high quantum efficiency, something that's approaching 1. Okay, large reason why semiconductors haven't been cooled. It's just, external quantum efficiency has to be close to 1, you know, in order to achieve that. Okay, so switching gears a little bit. I'm going to talk a little faster. Trivalent rare earths, there's other ones. This is known as a Deek diagram because Deek calculated the energy levels for rare earths in vacuum. You'll see the ytterbium here at the end. Lutetium is next, but lutetium has a completely filled shell, in which case there's nowhere for them to change or move or anything. So there's no luminescence or absorption. But you know, what we've been talking about is ytterbium. So it seems like anywhere where you can make use of like the ground state transition, okay, from first excited state down to the ground state, you should be able to do cooling. They all have that ability, right? So there's thulium, for instance, and there's erbium. There's just 3 at the end. Just stick to those. We should be able to do that here as well, okay? But why can't we do this in these other materials? Okay. So again, I'm just going to stick with the 3 at the end. Turns out these are the most popular ones for whatever reason. You know, high power, you know, burning off, you know, tattoos, you know, telecom, blah blah blah. But anyway, I think dentistry is a big one. Dentistry. But anyway, so you'll notice we go up and come down. That's it. That's all that happens. Okay. But once you have something more complicated, this is a result of only having one paired spin. Cerium is the same way at the other end of the list of rare earth opens. It only has one unpaired spin. Here, this is missing an electron, whereas cerium only has 1 electron. Okay, but okay, that's not really relevant here. Is this upconversion that may occur when you have multiple loads? Okay, so for instance, here's erbium. Let's say we're pumping at, you know, again, we want to pump in a wavelength that's longer than the average emission wavelength. So maybe we're pumping at 1560, 1570, 1580. Puts you up in here, okay? But that pump keeps coming in, okay? You're excited, but now look, this energy spacing and this energy spacing is about the same, okay? So what'll happen potentially is that instead of spitting out a photon, you absorb another photon and you end up over here, okay? Well, these energy spacings are such that this becomes a non-radiative process. And so the photon that gave you up conversion relaxes back down to the original state through the production of heat, okay? Thulium potentially has the same problem, okay? But if you take a look at the energy spacing here and here, that absorbing a second photon doesn't quite get you to this level, okay? And so this then means that our thulium system potentially can cool, and indeed it does. Erbium does not cool. Nobody's ever observed that should cool ever in the past, whereas thulium, yes. Other rare earths, ytterbium, as it turns out, has a pretty high solubility in most materials. You can put a lot of it in there before it starts to quench. Rare earths will also tend to cluster because, I mean, even in crystals, you know, you don't ever get like it's exactly this many lattice constants before an ytterbium, and then this many lattice constants. It's you know, it's whatever it happens to be. But anyway, is cooperative upconversion effects. So, for instance. Let's say we have a cluster of 3 erbiums. Again, all 3 are excited, so they're up at this excited level up here. And then, you know, what can happen? Well, again, they play hot potato, and so this one wants to get rid of its energy, gives it to this one, comes up to here. This one says, oh yeah, you can take mine too. It's getting too hot in my hands. And then again, you get another upconversion effect, and then all of this then trickles down the ladder to the original state, where you lost 2 photons in this process. Okay, and to heat. Okay, so so again, just to reiterate this, this is the last part of the talk. You know, we're putting in a photon, and we're getting a photon out that's just a couple % better, like more higher energy. Whereas all these other processes gobble up whole photons, okay, which is generally a bad thing if you want to do cooling. So again, what does real data look like? It usually looks something like this, where if you measure a change in temperature as a function of pumping power. So what will happen is, initially, it's room temperature, say, and as you're pumping, you increase the pumping power, you're creating more fluorescence, and there's more cooling. But then eventually, when you saturate the emitter, you no longer produce any more fluorescence. You produce as much as you can. You still have the unsaturated absorbers, like impurities and the quenching things that happen. And so at some point, this turns upwards and starts heating again. Okay, so you can't just crank on it. It's like at some point there's going to be a magic maximum cooling that you can achieve. Okay, and it just depends on what you want that number to be. Okay. I always point out though that you don't have to have lots and lots of cooling. It could be that some applications require a little bit of cooling. Just some management of temperature. Okay, so first, just again back to historical things. The very first demonstration of cryogenic cooling, NIST defines this as being below 120 K. I don't know if we can all argue about that, but made for a great article. It was in YB doped ytterbium lithium fluoride. You notice that this is a fluoride as well, just like the glass, the Z blend. I don't know if there's a connection. It's just that this turns out to have a very, very strong emission cross-section and a relatively short upper state lifetime. So it's very, very useful for this application. They used a thermal camera to measure changes, and of course, this was in a vacuum. Okay, this wasn't, it turns out that if you take your material that you're trying to cool and you put it in air, natural convection will kill you. Okay, it's just, basically, it's heating the air that's around, the hot air is rising, and the cooler air is sinking, and it's you're just getting air that's circulating and moderating the temperature. So they always have their stuff. This is the University of New Mexico group. They've always got their stuff in a vacuum chamber, along with something like toothpicks that are holding the material. Something very thin with very, very small touching surface areas to make sure that you don't get energy transfer from the outside into the crystal that you're trying to cool. This was all this work was headed by Professor Mansour Sheikh, who regrettably passed away last year of cancer. There was John West had there was a whole session on his behalf and stuff like that. Yeah, he unfortunately. We talk about a lot. I don't want to go in that direction. So record cooling, I pulled this out of one of the review papers that one of his former students put together. Record cooling was done around it's almost 10 years ago now, 91 Kelvin, and it still holds, at least as far as I could tell. So that's pretty cool. This is NIST's definition of cryogenic. This is the best that Peltier coolers can do, and then this is like liquid nitrogen, boiling liquid nitrogen is. Anyway, there's kind of that. And again, it's a testament to the purity of materials, and how well you can dope them and stuff like that. Applications, you wonder about applications. Again, this takes a lot of power to use cooling. One example of an application that they had was to cool using laser-induced fluorescence a mercury cadmium telluride detector array. Okay, they were able to cool down 135 Kelvin, but using 47 watts of optical power. Right. See, you wonder about this because this is going to heat, right? So this is making heat. You're using this to cool. So like out here is the laser that's heating or something, and you have this thing that's pumping this thing at 1020. It's yield just the same as always. It's their material of choice. There was a pretty crazy design. This is the actual crystal, and then there's like a thermal conduit, and that's coupled to the camera down here someplace. But it also takes 4 hours to get to the stable temperature. So it's kind of like you pull energy out fast, and then it slows down, and it takes longer and longer and longer to get to that point. So I don't know if they would have waited longer, maybe it would have gone to 130. So the fiber, I'll switch to fiber a little bit. The first cooling, demonstration of actual cooling below room temperature, net cooling, was also done in a ytterbium doped material, silicon doped fiber. But that was done in 2022, or 2020, I guess. This is done in air and atmospheric pressure. And so their cooling of only 50 millikelvin was observed. Okay, it's not a lot, but it proves the point. Okay, so the idea then is, if you're pumping and somehow you get gain out of this thing, you know, of course the gain has to be at a longer wavelength. Maybe there's some way that we can use this in a laser system, and I'll talk about that. Just as a side note, the only reported optical cooling in a semiconductor was reported in 2012, 2013 timeframe. What they did was they pumped cadmium sulfide nanoribbons at like 520, 530, 540. This is a range of wavelengths. And they claimed to observe 40 Kelvin of cooling. People spent years trying to reproduce that result, and nobody could reproduce the result. And so, of course, they reached back out to the authors. You know, we've been making these materials, and apparently the material's really crappy. Can we borrow some of yours to see like how this works? Well, then somehow magically those materials were lost. Okay, something is transformative of semiconductor cooling in semiconductors. Okay, I mean, semiconductor the carrier statistics are different. Okay, and the potential for cooling kicks the butt of glasses and crystals. You can theoretically down to like 10 Kelvin. Okay, so you know this result would be like, wow, this is like mind blowing. Okay, so why would you throw away the material? It's just, unless you were hiding something, right? And so there's this paper that came out. This is the general consensus, 2019. There are questions and concerns about the study that cast doubts on its validity. Okay, you just don't want to publish something and then have someone later publish something like this. That's terrible. We want to be open. If someone says, "Give me your stuff. Here's the stuff," and then later, okay, I made a mistake. That's fine. Okay, but this, that's not that great. Okay, so anyway, the analysis here showed that the external quantum efficiency of cadmium sulfide has to be greater than 97% in order to see cooling, and nobody's shown anything close to that apparently in that material. Okay, I promised the last couple slides. Other configurations, things where we can actually make use of this thing, not just cooling a camera or whatever for space applications. We can also make use of configurations that take advantage of this photon annihilation. So I've got this cartoon drawn up here. This is from one of my students' papers. But anyway, so this first one is normal operation. What do? You pump up to an energy, pump with a photon energy that's greater than where you expect to laze. This is now lasing stimulated emission plus spontaneous emission. Okay, that's heating. That's heating. This is the anti-Stokes fluorescence process. What we do is you go from the ground state to some steady state. We're picking the photon energy. You have some Boltzmann does something for you over here. You produce a photon, and that's cooling. It's an energy that's higher than where you started. Okay. But what if you did something a little bit different, where you kind of merge the two? Okay. So let's say what I'm doing now is I'm going to pump at a wavelength that's a little bit longer. Okay. I have to laze at a wavelength that's longer than my pump, energy that's less than where I'm pumping. Okay. But I can intentionally design the laser to not be that efficient and have it produce a lot of fluorescence. So I can also say, well, at the same time, I can absorb two photons. One of them is going to come out here. One of them is going to come out here. And if the energy difference is the same, I produce no net heat. Okay. That was first introduced in 1999 by NRL. We call that the radiation balanced laser. And then on campus, what we did is we took this another step. We said, okay, well, what if we did this a little bit differently, where we pump at a wavelength that's longer than where we want to laze. Okay, and this is confounding, is that you can't get gain. You can't get gain pumping only here. So what we do is you pump for a little while, you excite the upper state a little bit. It's not enough to get gain at a shorter wavelength, but then you come in with a higher energy photon, and you finish up the pumping process, and then you produce your laser signal. And this we call an excitation balanced laser, because we can balance the quantum defect this way through absorption emission. We don't have to worry about spontaneous emission. This you can imagine is inefficient, right? Because if we're putting in two pump photons, we get one signal photon and one spontaneous emission photon. We're losing half of our thing. Okay. But what you're doing in exchange is you're getting rid of the chiller systems that you need for these bulky, big, heavy, potentially lasers that you want to go in. This doesn't have that problem. Okay, anyway, it was Steve Bowman. This work in 1999 entitled Lasers Without Internal Heat Generation. I don't remember if the word radiation balanced laser shows up in here, but this is another cool piece of work. He demonstrated this, lots of other groups demonstrated this as well. This here is that the last example that I showed, the excitation balanced laser that this my group and Gary Eaton's group did, along with we used a fiber that Clemson had produced. It was a fluorosilicate glass. Okay, so just to conclude then, I'm a couple minutes over. Actually, I'm 1:58, so it started late, right? So perfect. Covered the history of fluorescence a little bit, anti-Stokes fluorescence and the second law of thermodynamics. Talked a little bit about the basics of laser cooling of solids, and then we talked about some of the applications, the drawbacks, and some of the things that stand in our way. Okay. Bottom line here is high purity materials, low quenching in terms of rare earth doped solids, and if one can make, if we can demonstrate cooling in a semiconductor, you will be famous, not infamous, hopefully. All right, any questions?